Okay, thank you. This is my last lecture here. Okay, so today I'll do something more sort of up to, right now it's quite a hot topic. I'm getting into it, running it. So, so this is something about enumerative geometry. And then when you start counting something, generating functions will have a modular form properties. So today's lecture is more like counting nodal curves on the K3 surface. So last time we did a bit of mirror symmetry for elliptic curves, but then here we'll try to count some nodal curves on the K3 surface. So what we'll do is, well, first we consider Dedekind eta function. This is a very classical thing. And then it's when Dedekind eta function was defined by Dedekind, I don't think he had any idea this function is so powerful in counting something. So this not eta function itself, but if you take 1 over eta of q, you can express this and then this infinite product, expand this, you'll get a partition function. Piece of 1n is the partition function of n. N is expressed as a sum of numbers in different ways. That's the piece of 1n is the partition function. So this function is coming up in physics very frequently. It's amazing. So we also consider this delta function, which is the 24th power of eta. So if you just take 24 powers, that's what it is. And if you expand it, it's all integer coefficient. Okay, so this integer coefficient has some meaning already, and then delta function is a modular or cusp form of weight 12 for this PSL2Z. Okay, so now so this eta function came up in the physics scenery by a theorem of Yau and Zastrow, and expanded by Brian Wren to a bit more general setting. So Yau-Zastrow theorem says you pick n, it's a non-negative integer, and m capital N sub n will be the number of rational n nodal curves on the K3 surface. So curves may have an n node. That's the kind of things you consider. Then the generating function, so you have all this sequence of numbers. So you cook up a generating function, m sub n, q to the n. Q is a formal parameter. Then this is just q over delta sub q. So if you expand this, one node has 24 curves, 2 nodes have 324 curves, and so on. Yeah, so this is amazing, and then try to understand this theorem. I went to their paper, Yau-Zastrow paper. This is entirely in terms of physics. Couldn't understand anything. But there is now a mathematical proof by Xi Chen, who was a student at Harvard. It is a fact. There is a proof, mathematical proof. Mm-hmm. Yeah. Now a bit of a generalization. You take a generic K3 surface, and C will be a holomorphic curve sitting on X, representing a primitive homologic class. So it's not a multiple of some homologic class. So for this setting, you need a primitivity. In the previous theorem of Yau-Zastrow, you don't need that. So any genus G and N satisfying self-intersection C2 divided by 2 is a G plus N minus 1. So that's the kind of curves you are going to consider. And then define N sub Gn. this will be the number of curves of geometric genus G having n node passing through G generic point in the linear system of C. Okay, so then you fix G and then run n. So f sub GQ is for fixed G, you consider this generating function. Okay, so if you do this theorem of Bryan and Wren, is that for fixed G, f sub GQ is this is a divisor function, Q is a formal parameter, and again delta sub Q is coming up. So the G2, the G's power divided by delta sub Q. Now G2 of Q, this is Eisenstein series of weight 2. It appeared last week also, but this is not normalized. Last week I had the coefficient 1 here, but it's not normalized. So that's and then sigma k is the divisor, sum of divisors dividing k, and then d is the differential operator. Okay, and if you do this, I also told you this is a quasi-modular form. G2 or Eisenstein series E2 is a quasi-modular form, and if you take a derivative, again it's a quasi-modular form. So this is FGQ is a quasi-modular form of weight 4G minus 12 for the full modular group. So these theorems are, counting functions expressed in terms of quasi-modular forms. This is quite amazing. I mean, so examples f0 of Q in the Bryan theorem. This is coincide. This is exactly the Yau-Zasloff theorem, and f1Q looks like that. F2Q. Also on these count all this. These are the integers counting those number of curves, nodal curves. This is really amazing theorems. But this is not what I want to do today. These proofs are quite involving, and then by itself it's another lecture. So today's lecture I want to do something, it's a Calabi-Yau threefold, elliptic Calabi-Yau threefold over the Pettus surface of degree 8. And I want to consider generating function of Gromov-Witten, but Gromov-Witten is too difficult to do anything. So something physicists came up, Gopa-Kuma buffer invariant. This can be computed. But the Gromov-Witten can be expressed in terms of Gopa-Kuma buffer. So this is a joint work with my former postdoctoral fellow Simon Laws. Okay, so I want to construct, so what is the del Pettus surfaces? Del Pettus surface is a smooth projective geometrically reducible surface whose anti-canonical bundle is ample. So minus Ks is ample. So this is a Fano varieties of dimension 2. And the degree is the self-intersection of the canonical bundle. And the degree moves between any integers, can take any integer between 1 and 9, including 1 and 9. So there is a classification theorem del Pettus depending on degree. What I want to do is here, you choose any integer r between 1 and 8, and then pick a generic point, P1 and PR from P2, and then you blow up P2 at this point, this R point. Then this S is the del Pettus surface of degree 9 minus R. Okay, so what I want to do is I want to consider the Pettus surface of degree 8. That means the degree 8. That means R equal 1. So just you blow up P2 at one point. That's what you want to consider. So the Pettus surface of degree 8. So pick a generic point, and you want to blow up this P2 at this point. So H will be the line not passing through this point P. Then anti-canonical bundle is 3 times h, and then self-intersection is 9h squared, it's 9. So now S to be the blow-up of P2 at this point P, and then E will be the exception divisor replacing this P. Then self-intersection of the exception divisor is -1. It produces -1 curve. So C be the blow-up map. Then you can compute the canonical bundle. Case of S is the blow-up map, induced blow-up map on KP2, and then adding exception divisor. So if you compute the intersection, self-intersection of the canonical divisor, canonical bundle, that's what you get. That was 9, and this is -1, so you get 8. So this is exactly the Repetto surface of degree 8. And these are rational surfaces, which is isomorphic to Hirzebruch surface. It's a very simple surface. And in fact, all these things I learned from Hirzebruch. He taught me in person. Yeah. So now I have a Repetto surface. I want to construct a Calabi-Yau over this surface. So what do you do? So I want to take elliptic vibration over this surface S, the Repetto, and then L be the line bundle on S whose intersection is 8, self-intersection is 8, and then you consider the global section. You pick element G2 from this here, and G3 from here. So G2 is a 4 times L, and G3 is a 6 times L. Now I want to consider the model over S defined by this equation. It's a Weierstrass vibration. Elliptic vibration is given by Weierstrass equation. So then canonical bundle you can compute relative canonical bundle together with S, and then this guy is it's L minus. So this whole thing, this guy X to be Calabi-Yau, meaning this is a Calabi-Yau condition. Canonical bundle have to be trivial. So if you impose this condition, Ks have to be L minus, which is equivalent to anti-canonical bundle is S. And Ks we computed before, that's minus 3h plus E. That's L is 3h minus E. H was the line. E is the exception divisor. Okay, so then 4L is this 4 times this guy, and 6L is 6 times this guy. So if you compute, well, then I want to already with this condition, these are the Calabi-Yau conditions. So 4L is this guy. What happened? 4L, and all these are computed. Now I want to introduce a coordinate so that I can express these guys D2 and so coordinate, introduce a coordinate, projective coordinate for P2, then G2 in terms of coordinate, this is inside 4L, it's a degree 12, and G3 is a degree 18. Now discriminant locus is a degree 36. Okay, so if you do this, X is an elliptic Calabi-Yau threefold over the Repetto surface of degree 8, and Euler characteristic is minus 480. So this proof is explained to me by Hirzebruch. So first, Euler characteristic of the Calabi-Yau can be computed by Euler characteristic of the discriminant locus together with cusps. And it's Euler characteristic of discriminant is just the minus degree of the canonical bundle. Canonical bundle here, Ks plus delta times delta. So this I have already computed what Ks is, delta is a 12L here. So if you compute this, 1056. And now number of cusps is given by the 4L times 6 intersection of these guys, which is it's 24 L times L. L was the line with degree self-intersection 8 So that's 192. So E of delta is this number, minus 672. So therefore, if you do this, you get minus 480. That's the Euler characteristic. But this is a Calabi-Yau, so I want to know what H11 and H21s are. This calculation I will be given. I will be using a theorem of Furek and Krustmann. This is in general. If you have a Delpetto surface S, this is a blown up of P2 at R point in general position. So this is degree 9 minus R. And then pi is the elliptic vibration with section. You have a section. So you can consider a group of sections. That's the Maunder-Bell group. Maunder-Bell group is finitely generated. So T will be the rank. T will be the rank. Then the X has the Hodge numbers. This part we already know. But H11 is the R number of points in general position plus 2 plus T. H21 is 272 minus 29R plus T. So that Euler characteristic is minus 540 plus 60R. So in our setting, R was just 1 because degree 8, so R was 1. And then also we can show that Maunder-Bell rank is 0. So the Hodge diamond is like that. So this 3 is quite, so this is the H11. H11 is just a Picard group, pick X. Okay, so this is what we have. So if you do calculation, you get Euler characteristic minus 480. So this kind of Calabi-Yau threefold has can be realized at degree 24 hypersurface in weighted project 4 space with weight 112812 defined by this equation. And then you can see that if you collapse x1 and x2, just fixing x1 over x2, and then defining this number to be just x1 squares, you will get the K3 surface. So already you have a K3 vibrations on this Calabi-Yau. So this we are going to use it later. Not only elliptic vibrations, but also K3 vibrations. Okay, so this is the Gromov-Witten Gopa-Kuma invariant. How are they defined? So we are trying to compute Gromov-Witten or Gopa-Kuma invariant for our case Calabi-Yau threefold. And these things are obtained by integrating against the virtual fundamental class of moduli space of stable maps. So we should know what stable maps are. So this is a moduli space of stable maps. So the X is our Calabi-Yau threefold. So for any integer g and n, you take g and n non-negative, and the beta is some fixed homology class. And define this set consisting of map C to X and P1, Pn, C. C is a nodal connected curve of arithmetic genus G. Okay, so it's a union of some curves. And F is a morphism from C to X. Class of C hits the given homology class beta. And the PI is a smooth point, a distinct smooth point sitting in the smooth locus of C. And then automorphism group fixing all PI have to be finite. And so stable meaning if this function f is constant in some of the component, this component must contain at least 3 distinct points. That's the stable map. So well, some literatures you put the bar here, I didn't do it. Put bar on top. It's compactification. So this is something called the proper Deligne-Mumford stack. These are stacky things. Okay, it's not even a scheme. It's just extremely singular space, having a coarse moduli space, and it's extremely singular. So the Gromov-Witten invariant is it's just you have to consider something called the virtual fundamental class. And then essentially, Gromov-Witten invariant is computed against this virtual fundamental class. This is something what count number of stable maps. But this is just a definition. You have no chance of calculating with this definition. No chance. Because first of all, virtual fundamental class, you don't know what it looks like. You have to do K-theory and all that, and then, but then it's not possible to compute. And this number, if a physicist says that this number, it could be integers. It's counting something, so have to be integers, but they actually not. In general, it is a rational number. So the Gromov-Witten invariant up to now mostly computed for genus equals 0. For g equals 0, they are integers. Okay, essentially that's the only thing you can do so far. Okay, so so once you define a Gromov-Witten invariant, of course you can consider generating function. Here for fixed beta we define this. Now you run the beta homology class and define this number. Then correlation function introducing Yukawa coupling, and then you now this g is this independent of beta, and g is running from 0 to infinity. So these are the functions you want to sort of characterize. What can you say? So these functions are extremely difficult. So I said that this Gromov-Witten capital N Gx, this number is not computable. So physicists came up with the crazy idea. If you consider more complicated invariant, little n g beta x, this is called Gopa-Kuma buffer invariant or BPS invariant, and then defined by this equation. Okay, so f of gq defined involving the Yukawa coupling we defined before. So if you define this number, and then if g equals 0, this g equals 0, then I expressed in this way. Okay, so physicist says this Gopa-Kuma buffer is easier to handle, and then they are supposed to be, these numbers are supposed to be integers. And then for Calabi-Yau, for Calabi-Yau 3-fold, Gopa-Kuma buffer is much easier than Gromov-Witten. So if beta is a primitive, then these guys are the same for genus 0. And then so n beta of x are just right for genus 0, because genus 0 is essentially the only thing we know how to do.
In this formula, you have q to the k beta.
Yes?
But beta is homology class, no?
Yes, I defined what it means q beta last time, right? Yeah. Okay, so we cannot do physics. We cannot do these calculations. What we can do is geometry. We are geometers. Okay, so geometry. We have to do geometry. So we go back to our Calabi-Yau 3-fold, and the repeated surface is isomorphic to the Hirzebruch surface F1, which is just a P1 bundle over base P1 with -1 curve as a section. That's the Hirzebruch surface. It's a very simple surface. So I'll fix a homology class of a fiber, which call F prime, and then homology class of section in S. So in this homology group, I fix this fiber and section, class of fiber and section. And then now X goes to S is P1, and then S goes to C is P2. I compose this, call it pi prime. I may not use this pi prime anywhere. So if you do this generic fiber of this elliptically fibered K3 surface has 24 I1 fibers, node, 24 node. So this, because this okay, so I fixed fiber and section. So now I write X of F will be one of these generic fiber, and X of C will be the restriction of X on the section. Okay, so X, if you restrict to section, this is a rational elliptic surface with 12 I1 fibers, 12 node. So now C double prime, E double prime is the classes of section and fibers in XC. This is a restriction of X to the section, so I can pick those. And now you remember, this Calabi-Yau threefold had H11 equals 3. So the Picard group is rank 3. So I want to define line bundles. L1 will be the O of S, L2 will be the O of this fiber, generic fiber, or L3 will be the restriction of X to the section C. So these are the embeddings, S embed into X. Iota 2 is the restriction of X to section embed into X. Iota 3 is the fiber embed to X. So X is like this, so fibers like this, sections will be like this. So that's what it is. And then so defined homology class C, pullback of C prime is the same as pullback of C double prime by iota 2. E will be pullback of E double prime. F will be the pullback of F. Okay, these are in the homology class. These are the line bundles. So lemma is that H11 is 3. So the Picard group has rank 3. So these line bundles L1, L2, L3 form a basis of the Picard group. And the classes C, E, F form a basis of a second homology class. So what's the intersection pairing? Intersection matrix. So if you see FE and L1, L2, that's the intersection matrix. And then rational elliptic surface XC has the intersection formula is 119, so gamma 11 together with E8. So this is a kind of, so we know geometry of this pick X and the intersection numbers. And so what we need is something called, in order to compute Gromov-Witten or Gopa-Kuma buffer invariant, we need something called the Netter-Lefschetz theory. With this, it's becoming everything trivial. So to compute Gopa-Kuma buffer invariant in the fiber-wise classes, we need Netter-Lefschetz theory. This is something about lattice polarized K3 surface, and the lattice so let's take lambda to be a lattice of rank R. So for this theory to work, rank is either 2 or 3. 2 or 3. So family of lattice polarized K3 surface or base curve sigma is a scheme. It's Z over sigma together with a collection of line bundles. So you take R line bundles such that for each point B in the base curve, fiber is a lattice polarized K3. So this XB, X is a Calabi-Yau, but if you take a fiber at B, then it's become a K3, and these are the generators for the Picard group, Néron-Severi group. So such a family, it gives a map and a moduli space of the polarized K3 surface, and intersecting the image of this map with a curve of certain divisors in the moduli space called the Netter-Lefschetz divisors. You will give that will give it the intersection of divisor against some cycles, give you Netter-Lefschetz numbers. So the Netter-Lefschetz divisors are determined by integer h, whose intersection class square of the class beta is 2h minus 2, and you have r integers d1, dr, which are given by this pairing. So this is so beta is in the homologic class. These are the line bundles. So these I'm going to compute for my Picard group. Okay, so such a divisor is called the Netter-Lefschetz divisor, and this is the notation. Okay, so define Netter-Lefschetz number. This is the divisor. You are against this cycle. So you are taking intersection with this divisor with this cycle. That's a number. And then NZ, D1, DR denote so this is Netter-Lefschetz. Now this is a Gopakuma. So defined by, so this is a Gromov-Witten stuff. It's genus 0 stuff. So beta is moving the homologic class, and then this DI is the pairing here. So theorem here is that invariant, this invariant, NZ, Gopakuma invariant, together with some number R0H and the Netter-Lefschetz number are related by this equation. What is R0H? This is some constant given by it's expanding 1 over delta Q into power series. That's the coefficient. So that's the so this is the sort of, this formula is the it's the basis for our computation. So now L1 and L2, these are I defined line bundles. Above, two generators of the Picard group. So I choose lambda to be the intersection matrix of the, this is L1, type. L2, L1, so that's what you get. That's the, so that has rank 2, this is the rank 2 lattice. And then I want to take this X, L1, L2, to be a family of lambda polarized K3s. But this has singular fibers. So if you do this way, it's singular fibers, so you have to resolve singularities. So X tilde be a resolution. Then you can compute the invariant of X and the resolution to be related by just the resolution, this invariant. This is the Netter-Lefschetz number for the resolution. This is twice of the singular one. So
because the singular fibers are just nodes or something?
Node, just a node. We are just considering a node. So the Netter-Lefschetz numbers, this is the magic. Netter-Lefschetz numbers are just a coefficient of modular form of weight 22 minus r divided by 2. In this case, r is 2, so that's modular form weight 10. There is only one of them. That's E10. E10, it's E4 times E6. If you expand this, that's what it is. Those are the Lefschetz numbers, Netter-Lefschetz numbers. Okay, so then to finally the Netter-Lefschetz number of this h was so you get h minus 4 times the delta is this determinant is missing here. Determinant here. It's this times this number Netter-Lefschetz number is just a scalar multiple of E10, and this scalar is given by the determinant of this minus 4 times the determinant of this. So this Hodge index theorem says that this guy cannot be negative, so this is a non-negative integer. Okay, so recap. recap. So to compute the Gopa-Kuma buffer invariant in the fiber classes, we look at the K3 fibration. And we took its restriction of L1, L2 to Kf. Then the intersection matrix became like that. And then we resolved singularity of this guy so that this guy became around the polarized K3. And then we took di to be the pairing. And the beta is a homologic class satisfying this. And then Gopa-Kuma buffer invariant was defined. This was the definition. And then the relation between singular ones and non-singular ones, singular ones and the resolution was related by this. Okay. So then the Gopa-Kuma buffer invariant is just computed by just computing the coefficient of E10. It's a scalar multiple of this guy. Because it really net left number, they had to relate, Gopa-Kuma was related in terms of net left was computed as a coefficient scalar multiple of this guy. Okay, so this part I don't need here. All right, so oh my God, it's so what's the generating function? So now we take beta to be C plus R F plus F prime. This was the fiber class, and C prime was the section, and M and R are any integers. You take that. And then because we can identify this guy's image inside the H2, because H2 SZ you can embed S with I1, you can embed S into X. So identify this. So you can write beta to be MC plus RF. So define for fixed beta, so this is the, you fix this beta, for homologic class is fixed, and then define the generating function using this Gopa-Kuma, and then you take this. Okay, so that's a generating function. Theorem. So this is the generating function of the fiber. We cannot do this all at once. We have to do fiber-wise, section-wise, and then you do the integer multiple of sections and add them to integer multiple fibers later. So this guy, the generating function you computed fiber-wise is a -2 E10Q divided by delta Q, which is expressed like that. And then if you do section, generating function on the section, XC, that's what you get E for Q, the delta Q. Expression is like that. So these guys are the meromorphic, this meromorphic modular forms. This is weight 10 minus weight 12. This is weight 4 minus weight 6. So it's a meromorphic modular form weight -2. And you can do this for eventually you want to extend this to the multiple of fibers. So this is also a meromorphic modular form of weight -2, but the group is different. Group is getting smaller. Okay, so how do we get this? I'll show you, I'll give you a proof for the fiber ones. This one is more complicated. Section ones are more complicated. So the proof is this is a modular form weight -2, because F plus NE, this is determined by integration against L1 and L2. So this Gopa-Kuma number is just integration. So this integrate against L1 and L2, you'll get then -2 and 1. So the generating function, this times Q to the n-1, you replace that. Now you can replace this with the resolved resolution. Gopakuma of the resolution. That's the half of resolution. So you take out half. And now you take n equals 0 to infinity. And then now h, this, if you get this number, then this was expressed in terms of netta deficit. R0h times netta deficit. So you replace this number with the netta deficit number here. And then the delta of h n minus 1, this is a determinant is, this is a determinant. Determinant is missing. Determinant is 2n minus 2h, which is non-negative. Okay, so we can write the generating function with half of h equals 0 to infinity, r0h, and then n equal h to infinity, this number, q to the n minus 1. So now I break up q, power of q into two pieces. So first I take out r0h, q to the h minus 1, and then remaining ones, minus 4. This was the deficit number was just scalar multiple of E10. So you replace with this. Okay. Minus 4 determinant of this, that's all computed. So if you do this, this is going to be half divided by minus 4, so minus 2, R0h, and n minus h, and E0 q to the n minus h. So if you write this out, that's what exactly you get. Because R0h was the coefficient of 1 over delta q. So that's the proof. That's the proof. That's the end for today's lecture. Because no time to prepare more slide. Okay.